And now a short summary of all of the reaction types for organic chemistry. Our most preliminary one is going to be the acid-base. You'll notice acids and bases get thrown around a lot. As far as I go as an instructor, when I mention acid or base, I'm referring to the Bronsted-Lowry acid and the Bronsted-Lowry base. And we'll talk about why I make that distinction later. You need to know these definitions. You should remember them from both first semester organic and, in theory, first and second semester general chemistry. Your Bronsted-Lowry acid is a proton donor, which is in reference to H, a hydrogen nucleus, so H+, or a proton acceptor, again, an H+ acceptor. This just stemmed from Bronsted and Lowry's definition of what they saw for particular reactions. The easiest reaction that most people could identify historically was looking at the acid-base reactions, where there was this transfer of hydrogen ions. Okay? So if we take a look at two possible example structures, hopefully you can see the structure in the red box is known as a carboxylic acid functional group. Go figure, its chemistry is that it is a proton donor. The proton that it would donate would be the hydrogen out on the end, not the ones attached to the carbon, because there's a larger difference in electronegativity between the oxygen and hydrogen than there is between the carbon and hydrogen. If we take a look at the next structure, what we've got is an amine functional group. While we have not yet talked about those until second semester, amines won't act as acids because the difference in electronegativity is not quite strong enough between those for it to release the hydrogen. However, it does have a pair of electrons that it can then share with a hydrogen. The hydrogen then gives up its electrons to the oxygen, and we've now run an acid-base reaction. Okay? So when we're trying to identify an acid-base reaction, we want to make sure that it is the only thing that occurred. Okay? Just the transfer of a hydrogen ion. We can take hydrogens on and off of a structure multiple times and do other things. If we do those other things, we'll typically classify the reaction according to those other things, not the acid-base characteristics. Okay? So given these two reactions shown below, what we would want to go through and do is identify the differences, which is an important characteristic to do with all reactions. So what I first see is that we have a hydrogen on that oxygen where one was missing. Okay? And I would also notice that, and actually, we'll change that up, a hydrogen appeared on our oxygen. You'll notice I drew that in blue. And a hydrogen disappeared from our other oxygen. So what ended up happening? Well, we had a proton transfer. The only thing that's changed is the location of that hydrogen atom. So we're looking at an acid-base reaction in that first one. If we take a look at the second example, you'll notice that we are missing that hydrogen from our iodine. So the natural instinct might be to say, well, we've got an acid-base reaction. But before we go through and do that, we need to evaluate what other changes occurred in the course of this reaction. Was that hydrogen merely accepted by our other structure? And yes, you will see that we did add a hydrogen. It's implied, but it is there. So we say, oh, well, it's an acid-base reaction. But is that the only thing that changed? Did we just change the location of the hydrogen ion? Clearly not, because there's also this new bond. Okay, so this is not an acid-base reaction. This gets a different name. This is technically an addition reaction, which we'll also talk about in a little bit. Okay, so that second one is not acid-base. So be careful with your delineations within your definitions. This brings us to the next acid-base definition. It shows up as Lewis acids and Lewis bases. This is actually a very, very broad definition that pretty much covers all chemistry in general. Lewis wasn't satisfied with the Bronsted-Lowry definition because it didn't explain other chemistries. For instance, that second reaction. Okay? If we're going to come up with a classification for reaction, it should really cover everything that we'd want to look at. So he instead evaluated it as an electron acceptor and an electron donor. Okay, and that's because when we do a reaction, we're looking at the transfer of the electrons, not the atoms. The atoms are merely moving around freely in space. At any given time, they could be a bond or not if rules are satisfied. And that rule being satisfied is that the electrons are being shared. Okay, so that's why he changed the definition to look at just at electrons. So be aware of that subtle delineation between that. And if we tried to break up that second reaction, we'd see that we're actually looking at a couple different steps within that, where the first step is an acid-base, strictly, a Bronsted-Lowry acid-base, and the second step is more of a Lewis acid-base reaction. Okay? So be aware of this extra definition that shows up. We may also see a tweak of our acid-base definition. So the Lewis acid-base one applies to everything. Okay, well that's way too kind of random. So if I throw out, well, it's an acid-base reaction, I don't know what acid-base reaction we're referring to. It could be Bronsted-Lowry. It could be a different one in the case of our second reaction here. So we'll also introduce this other idea of an electrophile and a nucleophile. The electrophile is an electron acceptor. The nucleophile is an electron donor. You'll notice that those definitions are identical to the Lewis acid-base definitions. But we're going to add one caveat. That caveat is that the electrons that are being shared are not being shared with a hydrogen ion. If it is being shared with a hydrogen ion, then the definition we'll use is our Bronsted-Lowry acid-base. Okay? So the electrophile nucleophile just allows us to separate out our Lewis acids from our Bronsted-Lowry away from our non-Bronsted-Lowry reactions. Okay? So how I would kind of look at the breakdown of all of our reactions, particularly our acid-base, is that our Lewis definition really encompasses two large parts: a Bronsted-Lowry definition and a nucleophile electrophile definition. The Bronsted-Lowry definition is what we will refer to continually as the acid-base reactions. The nucleophile electrophile reactions include your substitution, your elimination, and your addition. And realize within each of those reactions, we may see acid-base reactions show up at the same time within a step of the mechanism, but the overall reaction will still be called substitution, elimination, or addition. You'll notice I have subcategories coming off the substitution and elimination because we have subcategories of mechanisms of those reactions. We get the unimolecular, the bimolecular within each of those. Okay? And I've also added to the far right kind of the one invented by God knows what kind of goblin little things. We're looking at free radical reactions. Very, very powerful, because if we have no functional groups like an alkane, we can get it to react by going through a free radical reaction. We just need some crazy little goblin devil things to fix it for us. When we do our free radical reactions, we can also see, two different types come out of this, and that is a pretty massive typo there. We've got the substitution, which is true, but not elimination. We have addition. Okay? So two mechanisms for your free radicals, substitution and addition. So what are our other categories? Well, substitution and elimination are very closely related to each other, so I kind of group them together in one thing. They both have two mechanism types, unimolecular or bimolecular. So if we were going to look at these, we might call it an SN1 mechanism, meaning we're looking at a substitution using a nucleophile of the unimolecular type classification. Each of these mechanisms is controlled by four distinct categories. We have the substrate, we have the nucleophile and or base. Remember, nucleophiles and bases are effectively the same thing, it's just dependent on what they react with. We'll have a leaving group and we'll have a solvent dependence. So depending on what changes we make to each of these four things, we may end up seeing a substitution or an elimination. And then as a further addition on that, we may see a substitution type 1 versus a substitution type 2. Okay? So what we've got listed underneath each of these categories is the different things that we could be looking for to help us identify what type of reaction occurred. So when we look at our substitution side, we've got lots of 1s and 2's showing up in there, that's supposed to represent that statement being for that particular mechanism type. So if a nucleophile was strong, then we would expect a unimolecular, too many typos. If our nucleophile was strong, we would expect a bimolecular mechanism. If our substrate was very substituted, we'd expect a 1-type mechanism. If it was less substituted, we expect a 2-type substitution. Okay, so it's looking at each of these individual categories and saying, okay, what controls each? So you should be familiar with all of these things that kind of control and contribute to each of the reactions within these, both within the substitution category and the elimination category, and how they compete with each other. When we look at addition reactions, we're looking at how a pi bond interacts with a different substrate. Okay, that pi bond can either act as a base or a nucleophile, as we discussed in the functional group lecture. Okay, because we have that pi or that electron source. If our pi bond acts as a base, we end up going through the pseudo steps shown there. We're usually looking at this as a 1-step reaction, okay, but a 2-step mechanism typically. Okay. We'll end up with racemic products and we get rearrangements. Why do we get rearrangements? Well, as you remember from hopefully the SN1 reaction, carbocations get your rearrangements. Okay. If the pi bond acts as a nucleophile, it will need to react with an electrophile, and we may end up making, it's not quite an intermediate, but we may end up making another product. That product usually runs through a secondary reagent to then push us to our final organic product. Okay? So when we're looking at the pi bond as a nucleophile, they're usually 2-step reactions. So that means we would see in an overall reaction, if we drew it through the middle, going from beginning to end, we'd have step 1 and step 2. So 2 reagents to get through this. We will see stereochemistry potentially showing up in this. That's going to depend on the mechanism of those reagents. And they're very unlikely to do rearrangements. And that's because we're forming these products relatively immediate in between. Okay. The very last reaction type are free radical reactions. These are looking at the transfer of electrons as singles instead of in pairs. And we'll use fishhook arrows for these mechanisms as opposed to the full hook. So there's a fishhook, pretty ugly looking one. There's a better looking fishhook arrow. As far as our mechanistic steps, we've got initiation, propagation, and termination. That's going to be the same case for both substitution and addition. If we go through and look at our substitution category, we're looking primarily at alkanes as our primary reactive source, and we're looking at trading a hydrogen for a halogen, typically bromine. We can see chlorine show up, but that's pretty much it. And we're always going to try and form the most stable radical in that intermediate process. In our addition reactions, they will require an alkene because it's an addition. It's got to react with a pi bond. And they will usually use a peroxy radical initiator as opposed to light. When using HBr, we get a non-Markovnikov result. So it's a slightly different result than we would see from a standard addition reaction. So kind of interesting in that respect. So what do we do with all this information once we know all of our reactions? Well, we can identify a given reaction according to those types. So for that very first one, we could go through and say, well, potentially what we've got here is an addition reaction. Sorry, not an addition reaction. It's a bit silly of me to say. We don't have a pi bond, so it's not addition. We don't have any functional groups in our starting material, so we're looking at an alkane, which means the type of reaction we need to run would be a radical substitution. Well, with that information, I now know that I have to add light to get this initiated, and if I'm doing light, I'm probably going to do bromine. There we go. I've got the reagents, all because I understood what type of reaction occurred. So if we've got some information about that, we can propagate through this pretty quickly. We can also identify the starting functional group and then determine what reactions can come out of it, which I just did with the first one. If I have an alkane, The only type of reaction I can run with an alkane is a radical substitution. That is now going to limit what products I would expect and what reagents I can use. So having that information can drastically eliminate answers from a multiple choice test, say that you might find on an ACS standardized test. We can also look at the product to identify weak points. So when we talk about weak points, we have that carbon-bromine bond. So we could say, well, how do I form that? Well, the only way I can form that bond is doing some kind of substitution. Okay? So what I would want to use is some kind of reagents that allow me to do substitution. Okay? If I look at my reagents and I don't see a substitution, I can go back to my product and say, well, I could have potentially also popped off a hydrogen, which means I could have done an addition. So now I could go back and look at my reagents and say, did an addition work? Okay? I wouldn't look at, say, an acid-base reaction because it doesn't make sense with the initial bromine there. So it's kind of approaching each of these and seeing what options we have at each case and kind of whittling down, getting to a smaller and smaller option. So here's some practice. Identify the following reaction types. Those first two you should be able to do relatively okay. One is from first semester and the second is actually the tail end of second semester. And then that third question, much more difficult, giving you 2 steps to try and go through and process. You're going to have to think about each of those individual steps a little bit differently as you go through. And since I don't think I put a pause sign up, let's just go ahead and say pause now for me, please. Okay, let's go ahead and start with the purple one. We're looking at an addition reaction. We can identify the functional groups of an alkene becoming an alkane. So we lost the pi bond. If we lose a pi bond, we're looking at an addition reaction. If we go ahead and take a look at our blue one now, what happens as we translate across the reaction is we lost OH and H, which would suggest the loss of a small molecule, also an elimination. To verify, we'd have to look for that alkene. Sure enough, there is an alkene. You'll notice that the reagent that we've got circled there is a base. So what we ended up having to do was an acid-base reaction followed by the elimination. Overall, it's an elimination, not an acid-base reaction. If we go through and take a look at that last one, very tricky because we have to process through each of those individual steps. I would probably start this one by looking at the reagent here and say, well, it's a base or a nucleophile. If it acts as a nucleophile, I expect to see it on the product. Not on the product, so it's got to act as a base. So it's probably going to pull off a hydrogen, leaving a negative charge on this structure. So we can put our negative there. And then I'd move into step 2, where I add Rx. And we notice that extra R shows up in the product. Well, that R is a positive, and the X being partially negative. We can run a substitution reaction where we trade X for that big, bulky, chunky thing that we started with. So this runs as a 2-step reaction, where the first step is a simple acid-base reaction to generate a reactive structure. Then the second step is the actual substitution reaction to generate our final product. Okay? Hopefully that makes sense. If you got any questions, always feel free to ask.